Hello and welcome to Lecture 13 for the course ECE 252B, Spring Quarter 2020. This lecture covers Chapter 15 in the textbook entitled Variations in Dividers. So in this chapter, a whole bunch of miscellaneous topics about division will be covered. So we have so far covered basics of division in chapter 13, high-radix division in chapter 14. Everything else for these types of division algorithms we covered in this chapter. Chapter 16 devoted to a completely different division algorithm that is based on repeated multiplications instead of repeated additions. So that's completely different. And in fact, it's a method that's used extensively in modern high-performance processors. Okay, so let's now explore a number of ideas for designing dividers to augment our knowledge gained from the previous two chapters. The first idea is the idea of division with pre-scaling. So what does it mean? Here I've shown a portion of a PD plot, two of the four quadrants, showing the value of the divisor D going from some minimum value D min to some maximum value D max. And I've shown a couple of the overlap regions. At the top, you see the overlap region between choosing the quotient digit beta, which goes up to that line, and choosing quotient digit value beta plus 1, which begins at this line. And therefore, this is the overlap region. And if you remember from the previous lecture, we have to embed some staircase-like boundary inside this overlap region to allow us to make a decision between the quotient digit values beta and beta plus 1 for each range of the D values. So the decision line will be different here, then further to the right, and so on. And this complicates the decision process, and the narrower this overlap region, the more complicated the decision process becomes. Now we note that the staircase-like boundary that we put in there tends to have smaller steps towards the left end of this overlap region because it's narrower. And as we go to the right, the overlap region becomes wider, and therefore it becomes easier to make the decision. Okay, so this gives us an idea. What if we focused only on a small region of this PD plot, the shaded area, by forcing the value of D to be in a limited range, rather than going from D min to D max as usual? It goes from, let's say, 1 minus epsilon to 1 plus delta. So a very narrow region around 1, which is usually the max value. So if the max value is 1, I try to make the divisor D very close to this D max. So if D max is 1, I want to make the divisor in the range 1 minus epsilon to 1 plus delta, where epsilon is this distance and delta is this distance. So the benefit of this is that when I try to make a choice of quotient digit, I'll be limited in this gray area. And in that gray area, the choice can be pretty easy because a horizontal line can go through that, And in fact, often I have multiple choices for which horizontal line to use. And I can use the horizontal line, the boundary or threshold, that makes the decision the simplest possible. Okay, so how do I make D to fall in this limited range? I do that by scaling. Okay, so if I want to divide Z by D, I pre-multiply Z and D by some scale factor M so that D times M is in this region. Okay, because Z times M divided by D times M has the same value as Z divided by D, I will get the same quotient after scaling the two operands. Okay, of course, if I have to really multiply Z and D by the scale factor M, two multiplications, that's a lot of overhead. Okay, I do make the division faster because the decision process is now simpler, and therefore the quotient digit selection logic becomes faster and simpler. But how much do I save because of that to justify two multiplications? So these multiplications I try to do by shift and add so that they're not real multiplications. Okay, I'll show you examples of how this is actually implemented. Okay, so the idea is pre-multiply Z and D by some scale factor M and choose that scale factor so that multiplication by that scale factor involves shift and add rather than actual multiplication. Okay, so by doing that, then scaling of Z and D each requires a shift and add. So 2 cycles at the beginning to scale, and then K cycles as usual for doing the actual division. So I have K plus 2 cycles, but each cycle is now much faster because the decision process has been simplified. Okay, so this is the idea of division with pre-scaling. Let's go through a couple of examples just to make sure we understand what the pre-scaling process is. So suppose my unsigned divisor is in the range 1/2 to 1. So D min is 1/2. D max is 1. So here's my scaling process. Whenever D falls in the range 1/2 to 3/4, okay, in the lower half of that interval, 1/2 to 1, we multiply D by 1.5. And we know that D falls in that range 1/2 to 3/4 if D begins with 0.10. So 0 point, that means it's positive. The first one after the radix point is 1/2. And if the second bit was also 1, that would be 3/4. But I want the value to be greater than or equal to 1/2 and less than 3/4. So it should begin with 1, 0. So it's pretty easy to determine, to distinguish whether we are in that range. And then we multiply by 1.5. That's basically shift and add. Shift right, shift D to the right to get 1/2 D, and then add to D to get this. Okay, so the pre-scale divisor will be in this range. Okay, if the divisor is 1/2, when I multiply by 1.5, it will become 3/4. So that's the lowest possible value. If it's 3/4 and I multiply by 3/2, which is basically this, I get 9/8, which is this. So the values of D in this range are transformed to this range. And then from 3/4 to 1, I don't do any pre-scaling. So that's still in this range. 3/4 to 1 is a subset of that range. Therefore, in all cases, my scaled divisor is in the range 1 minus 1/4 to 1 plus 1/8. So this is 1 minus epsilon to 1 plus delta. So I've made it to be pretty close to 1 in order to take advantage of the wider overlap region towards the right end of the PD plot. And that was a very, simple toy example. I can be actually a little bit more sophisticated. And this example 2 shows that I can take the divisor in 1/2 to 1 and scale it differently for different subranges. So for the subrange 1/2 to 9/16, which is characterized by the starting bits 0, 1, 0, 0, 0, I multiply by 2. So the divisor is pretty small in this range. I multiply it by 2. For 9/16 to 5/8, which is when the divisor begins with 0.1001, I multiply by 1.5. For this range, 5/8 to 3/4, I multiply by 1.5 again. And for 3/4 to 1, in other words, a divisor beginning with 0.11, I multiply by 1 and 1/8. Of course, I can increase the number of these intervals so that I can choose different scale factors. Notice that all of these scale factors are such that I can multiply by them using shift and add. Multiply by 2 is simply shift. Multiply by 1.5, shift and add. Multiply by 1 plus 1/8, is shift and add. Okay? Once I do this in this example, so these are the new ranges of the divisor. So a divisor that was originally in the range 1/2 to 9/16, when multiplied by 2, will be in the range 1 to 1 plus 1/8, and so on. Multiply by 1.5 in these two cases, and multiply by 1 plus 1/8 in this last case. And then if you simply find the union of all these intervals, you get this. So the divisor will be in the range 1 minus epsilon. Epsilon is 5/32, to 1 plus delta, and delta is 1/8. Okay? As I mentioned, I can increase the number of these intervals because only one of these multiplications will be done. Okay? So it's not like I'm doing all of these. Depending on where my divisor falls, one of these multiplications will be done. So scaling still will involve one multiplications or one shift and add for the divisor and one shift and add for the dividend. And determining which of these needs to be done requires a simple logic circuit that basically looks at the high order bits of D and decides whether it starts with this pattern or this pattern or this pattern or this pattern, and therefore we know which of these scale factors to use. Okay, so this is an interesting idea to reduce the complexity of quotient digit selection and therefore making each cycle faster, although it adds a couple of cycles for scaling at the beginning. Here is the second idea, overlapped quotient digit selection. And as shown in this diagram, it's basically a replacement or an alternative for radix 4 division. In other words, instead of doing radix 4 division, we do radix 2 division, but try to determine 2 radix 2 digits in one cycle. How do we do that? Well, this part is basically a radix 2 divider. Partial remainder is kept in carry save form. We look at a few bits of the two components, and this oval box is basically a quotient digit selector logic. So the quotient digit selector logic looks at a few bits of the carry component and a few bits of the sum components and decides what the quotient digit would be. And normally in binary division, once the quotient digit -1, 0, or 1 has been determined, it's used to select one of these three values, forward it to the carry save adder, which receives the carry save partial remainder, and find a new carry save partial remainder for the next cycle. Now in this overlapped quotient digit selection scheme, we can actually do this. Okay, now this is the new partial remainder. I can repeat the same process, but then the latencies would add up. Okay, I have quotient digit selection, multiplexer, carry save adder, then quotient digit selection, multiplexer, carry save adder. In order to avoid this adding up of latencies and do things faster, on the side here I do some look ahead. In other words, there are three choices for the quotient digit. Okay, so I pre-compute the partial remainder in all three cases. So I don't wait for this quotient to be decided and for this carry save addition to take place, but right from the existing carry save partial remainder, I add d to it, I subtract d, and then here I don't do anything. That corresponds to quotient digit being 0. So in all three cases, I pre-compute the partial remainder, and I have it ready here. As soon as the quotient digit here is known, the first quotient digit, I choose the appropriate new partial remainder for the second half of the cycle, and then that value, sorry, not a partial remainder, the quotient digit. So for the three versions of the partial remainder, I compute the quotient digits. So the quotient digit is ready here for the second half of the cycle, even before the first half of the cycle is completed. Okay. So once the first quotient digit is known, I know which one of these three cases applies, and therefore I choose the appropriate quotient digit and do the second half of the cycle. So let's look at the critical path. So this second quotient digit selection, the only thing it adds to the cycle, see this part, CSA and quotient digit selection completely overlaps with here, because here I have quotient digit selection and CSA. Here I have CSA and quotient digit selection. So by the time I get here, and this multiplexer corresponds to that multiplexer on this part of the path. Okay, so the delay of this part of the circuit completely overlaps with the delay there. And then the only additional thing is basically this multiplexer and this carry save adder. Okay, so rather than start selecting the next quotient digit at this point, I started right up there by doing three versions of the quotient digit selection depending on what the first digit is, and then choosing the appropriate version for the next stage. So this requires only a little bit more latency per cycle and radix 2 division. And even if we did radix 4 division, it's still the case that the radix 4 division requires a longer cycle. And the radix 4 division is a little bit more complex to design and implement in this. So this is basically very standard components, multiplexers, quotient digit selection logics, 4 copies of it, a carry save adder. Okay, so it can be actually faster than a radix 4 divider. Now the question is, can we extend this to radix 8? Yes, we can, but as we increase the radix, the complexity grows exponentially. Here, because we did 2 digits at a time, we had 3 versions of the carry save partial remainder to compute. If we want to do 3 digits in one cycle, this will be 3 versions here, and for each of those 3 versions, so there will be 9. So the complexity grows by a factor of 3 with each additional bit that I try to predict in the same cycle. And of course, in the extreme, I can unroll this completely and determine all of the quotient digits at once, but then the complexity will be huge because it grows exponentially. So this is practical, perhaps for up to radix 8, not any further. So combinational array divider designed based on this principle will have exponential complexity. And given that divide is not a frequently used operation in many applications, we really don't need a very fast divider. Now in the next chapter, we see that once you have a fast multiplier, we can design a fast divider by taking advantage of that fast multiplier. So that's very attractive because with very small investment, additional investment in hardware, we can design a fast division algorithm using a fast multiplier. So that's basically what makes that approach very attractive. By contrast, the fully combinational tree multiplier, we saw that it requires order log k latency and order k squared cost, although theoretically we now know that it can be done in order k log k cost. That's only theoretical. So that word conjecture I should have actually replaced with proven. It's now proven, but it's not a practical design. Okay, so I can design a fast multiplier using having order log k latency and order k squared cost. By contrast, for dividers, we have theoretical results that say if you want to design a divider with order log k latency, basically asymptotically as fast as multipliers, you need a minimum order k to the 4th cost. So it will be much more complicated. If you relax the speed requirement just a tiny bit, and if you're satisfied with order log k, log k, then you can cut down the cost significantly from order k to the 4th to order k squared. Okay, I won't describe these results. These are basically results in complexity theory. You can easily look them up if you're interested. But the thing is, these results establish that divide is a fundamentally more difficult operation than multiplication. We can do asymptotically the same speed, but much higher cost, k to the 4 rather than k squared, or we can aim for the same asymptotic cost, but then the speed will be less. And even these designs are not really practical. Okay. Okay, so we do have combinational dividers known as array dividers. whose complexity is order, so going back to the previous slide, complexity is order k squared, and latency is also order k squared. So it's very poor latency performance. K squared is much worse than this. But we'll see why, despite this high latency, we are still interested in building array dividers for very similar reason that we had array multipliers. So this is a restoring array divider. It's drawn in this way, but I could have drawn it as a square array by simply shifting the rows a little bit to the left to make it into a square, and therefore easily laid out on a square chip area. Each of these square boxes in this design is shown here. It's basically a full subtractor and a multiplexer. Now the design of this array divider is directly obtained from this dot notation representation of the division process. So you see here there are 3 cells in each row, and there are 3 rows. That corresponds to 3 bits there in 3 rows. This is the zeroth partial remainder, which is an input to the top. So this is basically a fractional z, point z minus 1, z minus 2, up to z minus 6, a 6-bit fractional z, being divided by a 3-bit fractional d, point d minus 1, d minus 2, d minus 3, gives us 3-bit fractional q, point q1, q2, q3. Sorry, q minus 1, q minus 2, q minus 3. And then a remainder, which is a 6-bit remainder. Guaranteed to have 3 zeros here, and then s minus 4, s minus 5, s minus 6. So each of these cells basically corresponds to one of these dots. So when this dot is being subtracted from there, this cell does the job. When this dot is being subtracted from there, this cell does the job. And then there is a borrow. So this is the borrow chain going across a row. So here's what happens. The 4-bit z minus 1, z minus 2, z minus 3, z minus 4, so these 4 bits. From those 4 bits, I subtract these 3 bits using a 3-bit subtractor. And then that gives me basically the remainder. Now, if this subtraction result is positive, then the quotient digit will be selected to be 1. If it's negative, the quotient digit will be selected to be 0. Okay? So the quotient digit is 1. If this z minus 1 is 1, in other words, this 4-bit number begins with 1, therefore the result is guaranteed to be positive. Because I have a 4-bit number that starts with 1, and I'm subtracting a 3-bit number from it, the result is positive. So if that z minus 1 is 1, the result is positive. Or if the borrow out from the subtraction process is 0, if there's no borrow out, then again the result is positive. In those 2 cases, I choose the quotient digit to be 1, otherwise it will be 0. Now this quotient digit basically is fed back to the row, all the cells in the row, through this line. And it basically tells this multiplexer, if this digit is 0, then it says basically discard that trial subtraction result and use the old partial remainder as the new partial remainder. This bit is 1, meaning that the quotient digit was chosen to be 1, meaning that the trial subtraction result was positive, then we take the trial subtraction result and forward it to the next. Okay? So for the quotient digit of 1, the trial subtraction result is forwarded to the next row. For quotient digit of 0, the previous partial remainder is forwarded. And then this process repeats in the next row. Again, we do the trial subtraction. We choose the next quotient digit. The next quotient digit is 1. Then we forward the subtraction result. The quotient digit is 0. We forward the partial remainder that came in. Okay, so after 3 rows, which correspond to these 3 subtractions, I have the remainder, which is here, with 3 zeros attached in front of it. And I have the quotient, the 3 digits, 3 bits, or digits actually, of the quotient. Okay, so this is known as the restoring array divider because we use this multiplexer to restore the partial remainder to the correct value if the trial subtraction result goes negative. Now this is a non-restoring array divider. Once you understand the first one, this is not that hard. This one also has a bunch of cells, and these cells are now full adder and an XOR gate that allows us to do addition or subtraction. Remember that in non-restoring division, we need to do addition or subtraction in each cycle. So we do addition by sending 0 on this line. When 0 goes on this horizontal line, then basically this operand is forwarded and this full adder does addition. When this bit is 0, when this bit is 1, sorry, 1 XOR something is the complement of that thing, so this thing is complemented. And then this 1, which goes through the row, is inserted here as a carry in to make it 2's complement. Okay, so that signal has a dual role. First, it causes the complement of this operand to go through rather than the operand itself. And second, it inserts a carry in to account for that 2's complementation. Okay, so if Q0 is 0, by the way, in the first stage, we always subtract. The first operation is always subtraction, so there's a 1, constant 1 tied into that line to tell the first row to do subtraction. But then the subsequent rows, depending on the value of the quotient digit in the previous cycle, do addition or subtraction. If this bit is 0, 0 is sent through, and when 0 is sent in the next, so we basically forward the incorrect trial subtraction result, but then we add in the next step. If this bit is 1, if the quotient digit is 1, then we do trial subtraction in the next row as well. Okay, so these are basically circuits that look very superficially like array multipliers. In terms of structure, a square array of cells and local connections between those cells is similar to an array multiplier. But there's a major difference. Whereas in an array multiplier, the critical path is of length roughly 2k. If you remember, the critical path went through the diagonal, the k cells, and then through the bottom row, another k cell, 2k. The critical path of an array multiplier, I'll do it on this non-restoring version, but it's the same for the restoring version. The critical path, this red path that you see being drawn, goes through all the cells. So the length of the critical path is order k squared, which is awful, order k squared latency. That's because carries propagate in each row. The operation of the next row depends on the completion of operation in the previous row, because we need to know what the quotient digit was in the previous row, okay? And in the restoring case, borrows propagate throughout the rows, and it's the same thing, basically. So why do we tolerate this very high latency? Well, there are two advantages to array dividers. One is the regular structure and short wires. They're efficient to lay out in VLSI. And the second is that we can pipeline this design quite easily and be able to perform multiple divisions concurrently. So imagine I insert latches between rows of this design. Okay, and then once the first row has completed its job and the division has moved into the second row, the first row can start a new division operation. So if this is a k by k divider, you can have k divisions in progress at once using pipelining. Okay, we can have speed up methods, but they are usually not used in practice. So in order to reduce the length of the critical path from k squared, one thing we can do is to send the partial remainder from one row to the next, not in regular binary form, but in carry save form. So we don't allow borrows or carries to propagate, but we do carry save addition or subtraction. However, we do need the value of this quotient digit in order to know what to do in the next row. And in order to know that, we need to examine at least a few high order bits of that carry save partial remainder. Okay, we don't need to let carries to propagate all the way through, but we do need a few bits, maybe 4 or 5 bits, in order to be able to estimate what the next quotient digit will be, and then tell the next row. So that sort of defeats the regularity short wire advantage of this array divider, because I have to put those quotient digit predictors here, special circuits, that look at multiple bits. So there will be wires going along for this circuit that I put there on every row to look at multiple bits of the partial remainder. So even though theoretically it's possible, it's not used in practice. Okay, the next item in today's lecture is modular dividers and reducers. So what is a modular divider? A modular divider is basically one that performs this operation. So it divides z by d, takes the integer that is just smaller than that in case the result is not an integer, and then the remainder is z mod d. Now the difference here between this divider and a regular divider is that it's shown in this example. So if I'm dividing this negative number by 1.23, an ordinary divider gives me the quotient of -3 and a remainder of -0.07. Remember that the remainder in normal division has the same sign as the dividend. Here the dividend is negative, therefore the remainder of regular division is negative. Whereas the remainder in modular division is always positive by definition. Z mod D is a positive number, and therefore the quotient will be different in this case. So one way to implement modular dividers is to do a regular division and just check. If the remainder is positive, then you are done. If the remainder is negative, then you have to adjust this remainder and also adjust the quotient to get the correct result for modular division. In fact, when we do modular divisions, we are often only interested in this remainder and not in the quotient. Okay, so we can do a regular division. If the remainder is negative, just add the divisor to it. So 1.23 minus 0.07 gives you 1.60. So we do modular division often because we need the remainder. Okay, we need the modular remainder, not because we need the quotient. Now there is this algorithm called Montgomery modular reduction, which is a very useful, very important way of doing modular reduction, in particular in connection with multiplication. So when you multiply two numbers modulo m, so suppose your problem is to compute a times x modulo m, where m is a number that is less than 2 to the k. One way to do that is just do a regular multiplication, get this double width product, and then reduce it modulo m, but reducing a large number modulo m is tricky. It's not an easy thing to do because you have to figure out what multiple of m you should subtract. And that multiple can be quite large. So, it doesn't work if you go and then subtract m, see what happens. If the result is still too large, subtract another m. That doesn't work. It takes just too long. So you need a method for figuring out quickly what multiple of m to subtract from this double width partial product, and that's not an easy thing to do. An alternative is to do the reduction as you go along. In other words, when you multiply a by x, you develop all those partial remainders. For each partial remainder, reduce it modulo m, either before adding or after adding it to the running total. So that's one option. But then you need many modular reduction steps. Each reduction step is not easier than doing it at the very end, but still you need a large number. Okay, and then to make things worse is that if you do your multiplication by maintaining a carry-save partial product, a carry-save partial product doesn't give you an exact idea what the magnitude is, because the magnitude basically depends on all the bits of both components. You have to add them before you know how large your number is, and therefore what multiple of m to subtract from it. Okay, so because in carry-save numbers, the magnitude of the number is not easily established. You can establish an approximate magnitude by looking at a few high-order bits. But it's easier if we avoid that. Okay, so Montgomery's scheme, which I described without any justification or proof, solved this problem elegantly. Okay, so in order to multiply a by x modulo m, let's assume that axq and other values are k-bit pseudo-residues. In other words, they're not real residues mod m, but they can be greater than m. Real residues mod m are all less than m, okay? But pseudo-residues can be larger. So for example, m plus 1 is a pseudo-residue, mod m, which is the same as 1 mod m. Pick a number r such that r is equal to 1 mod m. Okay? Montgomery multiplication is a process that computes not a times x, but a times x times the inverse of r, modulo m. Okay? So take this for granted. I'm not going to justify it. So I'm going to describe a multiplication algorithm that computes a times x times r minus 1. So if I really want a times x, I don't want this value. This value is not what I want. I want a times x. This is what I do. Now I represent any number y as y times r. So this is known as the Montgomery code for y. Okay, so instead of representing y, I use y multiplied by r, a different number, modulo m. So it's the same width because I do modulo m, but it's a different number. Okay, this is known as the Montgomery code for y. So to do multiplication, you take the Montgomery code for a and Montgomery code for x and do Montgomery multiplication, which gives you this number. The two operands multiplied by r minus 1. The two operands multiplied by r minus 1. Okay, and this can be shown to be ax times r modulo m, but ax times r is the m code or Montgomery code for the product ax. Okay, so I start with the Montgomery code for a, Montgomery code for x, and then do Montgomery multiplication, and that gives me directly the Montgomery code for the product ax. So I can continue doing other computations with these Montgomery codes. So this is sort of an internal representation of values. And then at the end, I need to reconvert to standard representation. So how do I compute the Montgomery code for something? In other words, how do I compute y times r? Well, apply Montgomery's method to y and r squared. R squared is a constant. If I multiply y by r squared using Montgomery's method, y r squared times r minus 1 gives you y times r. So using Montgomery's multiplication method, I can initially encode all my numbers in m codes. And because Montgomery multiplication is efficient, as we will see, it's good. And then if I have yr at the end of some computation, and I'm interested in finding y, I Montgomery multiply, m multiply 1 and t. 1 and this value. So multiply 1 and yr times r minus 1, and that gives me y. Okay, so everything, both encoding and decoding, can be done using the Montgomery multiplication scheme itself. So what is the Montgomery multiplication scheme? It's shown here. So on the left, you see a regular multiplication of two numbers. If I want to do modulo 13 multiplication, I either have to reduce this final product, double width product modulo 13, which as I mentioned is a time-consuming and difficult process, or I have to do modulo reduction in every accumulation step as I go down these steps. Here is Montgomery multiplication for those two numbers. Okay, here's P0. Whenever the partial product is even, I just do as I do with regular multiplication. Okay, I right shift and add the next product. Okay, so when it's even, it doesn't change compared with ordinary multiplication. When it's odd, though, I have to do addition of 13. 13 is my M here. To make this even before right shifting. Again, in the next step, the partial product is even. I right shift this normal, and in this last step, the partial product is odd. So I add 13. So in each step that I get an odd partial product, I add 13 before right shifting. Okay? Because adding 13 does not change the modulo 13 value of the results. Okay? So now establishing that the value is even or odd can be done by looking at its least significant bit. So even if my partial products are represented in carry-save form, this decision is very simple. Just examine one bit. Whereas, if I want to establish whether this value is greater than 13 so that I subtract 13 from it before the next step, and if this is kept in carry-save form, that cannot be easily established because it depends on high-order bits. So the nice thing about Montgomery multiplication is the decision process in each step is a function of the least significant bit, which is readily available in carry-save representation. And then so if this partial product is in carry-save form, and I do carry-save addition, including the adding of 13, this is also done in carry-save addition, each cycle is pretty fast. I have these occasional adds, which means an extra carry-save stage, but still the process is almost as fast as regular multiplication, even though it's modular multiplication. Okay, so that's all I want to say for Montgomery multiplication. If you ever need to use it, you have to learn more about it. The information I gave you is not enough for practical use of the method, but now that you're aware, so under the name Montgomery multiplication, you can find in various books, handbooks, online sources, information about the multiplication method. Okay. Now the special case of reciprocation, if you remember for multiplication, we had the special case of squaring, which was easier. So one may naturally wonder, what is the corresponding special case of division? And first instinct would be to think that square rooting is that special case. Squaring is the special case of multiplication. Therefore, it's rather natural to think that square rooting is a special case of division. That's not true. So this is sort of a thought experiment. Suppose I have a divider that divides z by d. Okay, so z by d is this output. If d is square root of y, then the output will also be square root of y. If I divide y by square root of y, the output will be square root of y. So this gives me an idea. What if I connect this output to this input and let, signals to sort of settle into some final steady state. And therefore, if I input y at that point, the input y, I get square root of y because these two things are equal. I force them to become equal. Okay, unfortunately, this scheme does not work in general. It may work for certain dividers, certain implementation of the divide algorithm, but in general it doesn't work, and you may get basically instability, signals basically fluctuating wildly before becoming stable, or in fact never becoming stable, and sort of destroying, burning the circuit. So square rooting is not a special case of division in the same sense that squaring is a special case of multiplication. However, reciprocation is a special case. See, in squaring, we have just one input that is given to both inputs of the multiplier and one output. You give it y, gives you y squared. In reciprocation, you also have one input. The other input is a constant, 1. And then it gives you the reciprocal of y. So reciprocation can be viewed as a special case of division where one operand, z, is equal to 1. Now, the question that arises, is reciprocation any easier than a full-blown division? The answer is no if a conventional digit recurrence algorithm is used. If you use a conventional digit recurrence algorithm, you need the same k iterations regardless of whether the z is, an arbitrary number or 1. So you can't speed it up in that sense. However, there are special methods for speeding up reciprocation. Some of these we'll see later, but this is one method that I want to discuss here so that at least you have been exposed to one way of computing reciprocals faster than doing division. This is based on a two-stage process where the first stage computes the reciprocal using ordinary divide algorithm approximately. So if the reciprocal has k bits, this one may compute only up to k over 2 bits. So k over 2 iterations rather than k iterations, okay? So it takes less time to do that. And then the second stage of the circuit basically refines that approximate value of the reciprocal to give you a full precision reciprocal with double the precision. So this has k over 2 bits of precision. This has k bits of precision. And that is done based on using this equation. So if q is the approximate reciprocal, and if you plug it into this equation, then you get the more exact reciprocal. And this equation can be computed in parallel with the digits of q emerging from this part, so that the time latency of this part, which is k over 2, completely overlaps with the time latency of this part, which receives the digits of q, the k over 2 digits of q, and does k over 2 cycles of refinement. Okay, we will understand this equation much better in the next lecture because we use it there for division. Okay, so for now, just accept the fact that this equation refines the approximate reciprocal, and then we'll justify it next time. Okay, so this takes basically half the time of a normal division to compute the reciprocal. Of course, it has more hardware because here's a divider basically that you use it for k over 2 cycles. So the hardware is the same as a divider. And this additional hardware basically allows us to do things twice as fast. Okay, as I said, when we justify this equation, refinement equation for the reciprocal, you'll understand the scheme better. Okay, the last section in this chapter deals with combined multiply-divide unit. Now, in high-performance computers, we almost always have separate multiply and divide units because we do need the performance benefit of having both so that we can perform may even have two multipliers and one divider so that we can do 3 operations at once. Okay, but for lower end of the performance spectrum, we can combine a multiplier and divider given that the two hardware implementations are very similar. So on the left here you see a multiplier. On the right you see a divider. You see the components are pretty much the same. They both have an adder. The registers are the same. You have this quotient digit selection logic here that does not exist here. Here you have right shift of the registers. Here you have left shift. So basically this gives us an idea to combine these two circuits into one universal circuit that can do both multiplication and division upon command. So the command goes into the control unit for this circuit that tells it whether to multiply or divide. If it has to multiply, it uses these components the way a multiplier works, including right shifts and so on, taking the multiplier bit and using it to decide what to do. And if it's told to divide, it uses the hardware according to divide iterations, computing the quotient digit, inputting it into that register, and so on. Okay, so we sort of save hardware. Of course, the control unit is now more complicated than that of a multiplier or divider, but we save duplication of the adder and of these registers. There's a slight speed penalty because of the more complex control unit. Both multiply and divide may be slightly slower than if we implemented them in dedicated multiply divide unit, but that's usually tolerable because of the savings. Okay, similarly, array multipliers and dividers have similar structures, although the cells are a little bit different. The structures and connectivity are roughly the same. So this gives us an idea to build a universal array that can multiply or divide, okay, according to the command given to it. If we ask it to multiply, it basically uses the cells in this way. And if we tell it to divide, it uses the cells in that way. And in fact, we haven't talked about square rooting yet. It's possible to combine square rooting function into the same array, because when we talk about array square rooters, in a few lectures, you will see that the structure of an array square rooter is also similar. So each cell within the array can act as a modified adder or modified subtractor based on control input values. And as I mentioned, in some designs, both squaring and square rooting functions are incorporated into this array to make it truly universal. Okay, that's all I wanted to say for chapter 15 topics. Next time, we'll see a very interesting division algorithm, division by convergence. Actually, two algorithms that do division by repeated multiplications rather than repeated addition subtractions. And it leads to pretty impressive performance for division. So until the next lecture, stay well and healthy, and I'll see you in lecture 14.